So if we're given the sequence an e to the 1 over n, and we want to determine if this sequence converges or diverges, just remember we have to take the limit as n approaches infinity. This is all pretty simple. Like I said, we've been hitting series pretty hard, and sequences, we're reviewing it all the time as an effect. So if we take the limit as this sequence goes to infinity, we can just apply the limit directly, no issues there. I mean, really, you can kind of look at this as taking the limit of this 1 over n. So you're taking the limit of that exponent only. And that would give us e. So this is limit as n approaches infinity. So this would be e to the 0, which equals 1. Right? So therefore, this is convergent. The sequence is convergent to 1. Okay, so just remember the difference between, I think the confusion between the convergence of sequences in series is that when a sequence converges to a number other than 0, it still converges. But for a series, if you had series an, which for this case would be series e to the 1 over n, if this sequence an doesn't converge to 0, then your series diverges, right? So just kind of get that definition straight. And if you really stop and think about it, it makes sense, because if we're saying that our sequence e over 1 to the n is converges to 1, that's saying this is a sub 1 plus a sub 2, a sub 3, and then when we take it out to some large value of n, this is almost equal to 1 plus something that's almost equal to 1 plus something that's almost equal to 1. So we're adding basically all of these terms that are almost 1 towards the end of this series, so this thing's going to diverge. So just remember that difference between your sequence and series, right? So again, that's just kind of an aside there, but this sequence an is convergent to 1. Okay, 2. Any questions on that? Hope I didn't confuse anybody with that definition. All right, so number 2, we have a sequence 2n minus 1 factorial over 2n plus 1 factorial. So we want to determine whether this sequence converges or diverges. Just kind of intuitively, we can see that the denominator is bigger, right? So intuitively, we should think that it is convergent to 0. But if we were to actually write this out, let's take the limit as 2n plus 1, or 2n minus 1 factorial. And now, since the denominator, we have a couple terms in addition to the numerator. So if we start with 2n minus 1, we can factor out the next 2 terms, which is 2n and 2n plus 1, right? And then we'll have the 2n minus 1 will still be a factorial, right? We'll still have all the terms preceding 2n minus 1. So we can cancel out these 2 factorials, and we're left with 1 over 2n times 2n plus 1, and this is 0, right? Okay, there's a couple special limits that you might run into. And I know we've talked about one of these, n over 1 over n. So this one, if you apply the limit directly, so this this is your AN. So this sequence, if we want to determine whether this is convergent or divergent, we take the limit as it goes to infinity. And if we apply the limit directly, we get infinity to the 0 power, right? It's something that approaches infinity and something that approaches to the 0 power. So we really don't know how this behaves from looking at this. However, we can use a little trick. We can do E ln n to the 1 over n, right? E to the ln is the trick. It's really not doing anything to it. You know, if you take E to the ln of something, it just goes right back to what's in the parentheses. But by doing this, well, first we can write E to the exponent out front. Ln, this exponent here can come out front, right? That's one of the properties of natural logarithms. So we can have 1 over n ln of n. And if we apply the limit to this guy, we have infinity over infinity. This is a case, so we can use L'Hopital's rule. So this will be 1 over n over 1, right? The numerator was ln of n. The denominator, we have n. So if we take the derivative, we get this. Now if we apply the limit, we'll have 0. So we still have the exponent in front, or exponential in front. So it'll be e to the 0, which is 1. So our limit of n to the power 1 over n is equal to 1. And that's kind of a special definition you can just use as a definition. Like if you were to see that and you recognize it, you can just quote it as 1 if you were to use that on an exam or something. But as you can see, you can use this little trick here, exponential raised to the power ln, then you can take care of that. Also, there's another case. So if you had the sequence n over 1 plus n to the n, you could do this. You could use the same technique, e to the ln, right? And then take the limit. And you'll find that this one will reduce to one over e. So just use the same technique for that one. I don't want to spend time on this one since we just went over that technique. Okay, so we have, after sequences, we've done all kinds of series tests. I've even given you a handout on it. So the last thing we really talked about was conditionally convergent, absolutely convergent, or divergent, right? So this first problem, we have n equals 1 to infinity, negative 1 to the n. And this is actually the worksheet that I posted online. So all of these problems will be on B courses with the solutions as well. So this one, we're going to want to check if it's convergent or absolutely convergent, conditionally convergent, or divergent. So we can use the ratio test, the absolute ratio test. Generally, that's what you would be using, although you could probably use the root test for many of these applications when you have all of your terms raised to some sort of the nth power. And also, I mean, you can use any of the other tests as well, integral test, limit comparison test. If you use absolute value and it converges for that case, then it'll be absolutely convergent, right? And again, one thing to note, if something is convergent absolutely, you do not have to check the case without the absolute value because it will automatically converge for that case as well. Okay, so for this one, I'm going to choose to use the absolute ratio test. We've been just calling it the ratio test so far. I just dropped the absolute value terminology out of it, but obviously the way we've been applying these, we've always been applying the absolute value for the an plus 1 and the an term. So the absolute value ratio test is going to be an plus 1 over an, right? So we have the limit. So if we have the absolute value, we can drop this -1 to the n, because that term is what's making it alternate and switching back and forth from negative and positive. And since we're taking the absolute value, we don't need that. So we're going to have n plus 1 plus 1, so that's n plus 2, times 3 to the n plus 1 power, all absolute value, over 2 to the 2n plus 1. So that's stuck in between the 2, so it'll be 2n plus 2, right? And then we have to add this 1, so it'll be 2n plus 3. Is everybody okay with that? Okay, so now we multiply, or we divide by an, absolute value of an, which is the same thing as multiplying by the reciprocal. So we have 2 to the 2n plus 1 absolute value over n plus 1 times 3 to the n. So we can cancel out 3 to the n with this 3 to the n. We can cancel out this guy with 2 to the n, and one of these we can cancel out, so it'll just be 2 squared in the denominator. So we'll have limit as n approaches infinity over of 1, or n plus 2 over n plus 1. What else is left? 3 divided by 4, right? And I'm going to drop the absolute values here because everything's positive anyway. So looking at this first term here, we can see that if we take the limit of this guy, the only term that matters is this n, and this essentially just goes to 1. So we're left with 3/4, right? And I think some students would stop here. Just don't forget, this is equal to your L, right? And this converges when it's less than 1. And since it is, we can say by absolute ratio test, absolutely convergent. And we don't have to check the case without the absolute value, because as I've said, if something is convergent with the absolute value, then it will automatically be convergent without the absolute value. Okay, any questions on this one? All right, so moving on. We have this case here. So we have -1 to the n. So we can see that it's alternating. So I'm gonna check to see if this is convergent right away by the alternating series test. So what are the conditions for alternating series test? Well, we have to have the limit go to 0, right? So that's one of the conditions. So we'll check to see if our an, this is our an, to see if our an goes to 0. So limit of an, does this equal 0? Well, we have a -1 here, and remember there's a theorem that says if the limit of the absolute value of an equals 0, then the limit of an also equals 0, right? And since this is what we're interested in to see if it's equal to 0, we can simply apply the absolute value to our an here. So we'll be left with root n. So the absolute value of this will be ln of n, and we can drop the -1 to the n, right? So does this equal to 0? Well, if we apply the limit, this is infinity over infinity. Let's apply L'Hopital's rule. So this will be 1/2 root n over 1 over n, right? And then before evaluating, we can do some cancellations here. We can bring this 1 over n to the numerator and combine it with this guy, right? So this will be 1/2 root n, and this goes to infinity. So our limit of an does not equal 0. So this actually fails the divergence test, which means that it also fails the alternating series test. So this is divergent. Divergent by nth divergence test. Okay, so any questions on that one? So ratio tests you generally want to use when you have exponentials, right, or factorials, because the ultimate goal of the ratio test is to cancel a bunch of terms out, right? So anything with factorials or exponentials, you can use. It would be wise to start with the ratio test, but that doesn't mean that's always the rule. It's more of a strategy in choosing which one to use first. You could have definitely gone with the alternating series test for this one too, but because I'm seeing all of these exponentials, that's why I lean towards the ratio test first in order to see if that would produce a good result for us, right? So again, just kind of use these as general guidelines, but you may have to at times use different tests to see if they actually work. Sometimes they won't work. So, and for this one, if you use a ratio test, you would have square root of n plus 1, ln of n plus 1 on top and bottom, and you're really not going to get. You're just going to keep taking derivatives of weird terms, and nothing's going to cancel out. So again, a rule of thumb is if you have exponentials and factorials, those are good to use ratio tests. But since this one doesn't, and there's clearly a -1 to the n, an alternating series term, that's why I knew to use the alternating series test for this guy right away. So let's look at the next one. N equals 1 to infinity cosine of 3n over 1 plus 1.2 to the n. So I know I just said when you have exponentials, use the ratio test, but now we have something with a cosine. And remember, when we have trigonometric functions, it's usually bounded by a couple limits, right? Cosine, sine, tangent, all these trigonometric functions are bounded by 1 and -1 or 0 to 1, depending on how you look at it. And since we're trying to do absolute values, see if this is convergent absolutely, I'm gonna choose to do the apply an absolute value to this guy first and see what happens. And again, because there's a cosine of 3n, I'm thinking let's use either a comparison test or limit comparison test, right? Because I know that the cosine is bound by some limits. So we know cosine of 3n, the largest number this can be is 1. So this has to be less than or equal to 1. And since, again, I'm taking absolute value, I don't have to look at the negative one, right? And if I wanted to compare this with something, if I needed to choose a Bn, the denominator, the only thing that's really relevant is this 1.2 to the n, right? I can kind of ignore this 1. So my original an is 1 plus 1.2 to the n. And my bn would be 1.2 to the power n, right? So is this inequality still true if I put that denominator? Right? Is this bn still always greater than or equal to? It should be, because we're comparing this 1.2 to the n, 1.2 to the n, but this one also has a 1 that we're adding to the denominator, which makes your overall fraction smaller. So at most, this was 1. So even when we're looking at the biggest possible case for this cosine 3n, we have this extra 1 term that we're adding to the denominator. So it drives your entire fraction smaller. So your bn is always going to be greater.
Can we also do 1 over 1 plus 1.2 to the n?
1, you said 1 over
1
plus 1.2 to the n. Yeah, but how do you know how? I mean, this makes it a little bit more complicated, right? Because this right away is a geometric series, right? And then now we can't just simply say that this is a geometric series now, right? So it's kind of you want to choose a bn that you can definitively say how it behaves, right? I don't really see how we can manipulate this guy to make it look like any form of series that we know how to deal with, which is why we usually drop a constant or smaller order terms and just leave either an exponential or a polynomial or a variable to some integer power, right? So, or actually, it doesn't even have to be an integer power, but just one variable with the highest power is usually what we keep. So again, so I kind of gave it away here, but this 1 over 1.2 to the n, this is the same thing as 1 over 1.2 parentheses n, right? And what do we know about the geometric series? When does it converge? So we know this is a geometric series because we have this term r, and we're multiplying for each n that we're indexing, we're multiplying it by r, right, itself. So we're going to start with 1. The series is going to look like 1 comma 1 times r comma 1 times r squared, so on and so forth, right? This is the sequence. So when do we know when the geometric series converges? So we've used this definition in our series portion, but that's when r is less than 1, right? So when r is less than 1, your geometric series converges, right? Sorry, when I was doing this, I meant 1 plus r squared plus r cubed. It should be plus, since we're talking about series. So we know that 1 over 1.2, 1 over 1.2, this is less than 1. Therefore, Bn, series Bn will converge, right? So then can we say anything about our series An?
Oh, then the other series also converges, and therefore the series converges absolutely by the comparison test?
Exactly. So since we can compare, since we're comparing both AN and BN, our series AN will also converge. And since we are dealing with absolute value, it will converge absolutely. Okay, so now I have the next series of questions is dealing with radius of convergence and interval of convergence of the series. So this is kind of more recent. So if we have -1 to the n, x to the n squared by the n. Okay, so if we want to find the radius of convergence, we always either use the ratio or the root test. Okay, generally the ratio test always will work. Sometimes the root test will work when you have everything to the power n, but I'm not going to use the root test because this n squared term doesn't have something to the power n. So this will just get really messy when trying to use the root test. So I'm going to use the ratio test, the absolute ratio test, right? Absolute ratio test to find. So again, I'm looking for radius and of convergence and interval of convergence. So we take the limit as n approaches infinity of a n plus 1 over a n. And I'm going to drop the -1 to the n power. So we'll have x to the n plus 1 over n plus 1 squared times 5 to the n plus 1 divided by a n. So I'll have x to the n over n squared times 5n. So make some cancellations. Oh, actually, I can't cancel that. Cancel this. I'm left with, let's see, x times n squared over n plus 1 squared, also divided by 5, right? I have a 5 to the 1 power here. So if I take the limit of this, I take the limit of this guy here, right? I have the highest power is n squared, the highest power in the denominator is n squared, so this is going to go to 1. So I'm just left with absolute value of x over 5. And again, this is the limit, right? When we're doing the ratio test, this is our limit, and this has to be less than 1. So that means our radius of convergence, remember the general formulation is x minus a less than r. So we need to get it in this form. So I'm going to multiply the 5 over, and I'll have this. My a is 0 in this case. So my radius is going to be 5. Now, if we want to find the interval of convergence, we're going to have to evaluate at the endpoint. So we get rid of the absolute value, right? And then we're bounded by -5 and 5. So we plug these endpoints back into our original series here. And we can use our other tests to see how that behaves. So let's try plugging in -5. We'll have sigma -1 to the n, -5 to the n, over n squared 5 to the n equals 1 to infinity. So we can make some cancellations here. This 5 to the n can cancel out with that, but I'll be left with, so this guy here is -1 to the n times 5 to the n, right? So that 5 to the n will cancel out with this one. I can merge this -1 to the n with this 1 to the n, which becomes -1 to the 2n. So what is -1 to the 2n? That's always going to be positive because I have this even exponent. So I can just get rid of this and say it's 1. So now I'm left with the series sigma of 1 over n squared, n equals 1 to infinity. And of course, this is a p series. P equals 2, which is greater than 1. Therefore, this is convergent. So we know that we're going to have an equal sign here. And now we check 5, our other endpoint, n squared, 5 to the n. So this is for x equals -5, x equals +5. And again, we can cancel out this 5 to the n. Now we're left with -1 to the n over n squared. And really nothing changes here. We could look at it as the absolute value of this thing and say it's a p-series convergent, or we can just apply our alternating series test, right? The limit goes to 0. Limit of an goes to 0, right? And it's decreasing. All of our terms are decreasing. Basically 1 over n squared. So 1 over n squared is decreasing. So therefore, this is convergent. So therefore, convergent by AST. So now our interval of convergence is going to be -5 to 5 inclusive. So again, be careful if they're at, you know what it means when they ask for interval of convergence versus radius of convergence. Radius of convergence is a bit easier. And generally on an exam, I think they asked more radius questions, coupled with finding whether a series is convergent or divergent. I think it's a little bit faster that way, but just know that if they're asking for the interval, you always have to check the input. So any questions on this one? Okay, let's see. So I'm gonna skip the next one and go to Maclaurin series because it looks like we're starting to run out of time. Okay, so we'll look at one of the Maclaurin series problems. We have f of x squared over 1 plus x. So now we need to find Maclaurin series and the radius of convergence, an r, right? So Maclaurin series, again, this just means when it's centered about 0 or when a equals 0. And there's a couple ways you can do this. One I call kind of brute force method, where you essentially just find the nth derivative at a, so in our case it'd be 0, x minus a to the n. So you essentially find all of your derivatives, so evaluated at a. So you would start with the 0th derivative, which is just f of x. So you would find f of 0 and f prime of 0. And you would do this for a few terms, usually 3 or 4 terms should suffice, right? So you would find this, and then essentially just plug into this formulation here. So you would have this over 0 factorial, x minus 0 to the 0, right? So you would do this until you find a pattern, and then you can express this as a summation here on the left-hand side. So you could do this, or since we know our definition of the geometric series, so we start with geometric series, and this is a little bit faster, I think, and more eloquent than trying to do it this way. Geometric series. So So we start with 1 over 1 minus x, and this is equal to the sum of x to the n equals 0 to infinity. So here's our a equals 1 in this case. And no, this is not the same a as this a, okay? So this is, it might be a little bit confusing, but this is a different a. This is the first term of our geometric series a, okay? So in our case, we're starting with this geometric series where a here is equal to 1. And this is 1 plus x squared plus x cubed plus dot, 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 right? So now we're just trying to get it into this form, which means we can replace x. So notice this is 1 minus x in the denominator, but we want 1 plus x in the denominator. So we can rewrite this as 1 minus minus x and replace our x's with minus x's, right? So this would be 1 minus x squared. So this would be plus x squared minus x cubed. So this alternates, right? And you can see that here when I replace x with negative x. This is the same, this is the equivalent to negative 1 to the n times x to the n, right? So it's alternating. And now we just have to multiply the numerator by x squared to what we just found. So x squared over 1 minus x is going to be, so if I multiply negative x to the n times x squared, so I've already split negative 1 to the n, so I can write that out here. And if I combine the bases for x to the n times x squared, I'm going to have x to the n plus 2 equals 0 to infinity, right? And if I wanted to write out my right-hand side, I would have x squared minus x cubed plus x to the 5th minus x to the 7th plus dot, 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 right? So how do I find the radius of convergence? Well, this is my r. Absolute value of r has to be less than 1. So negative x less than 1. So x is still less than 1. So my radius is unchanged. It's still 1. Okay, so I will end it here. So the sheet that I posted, or I will post on B courses, has a few more questions on there. I'll post the solutions to that, and I'll stay after for the next hour so to answer any questions about this or any other questions that you might have on homework. So thanks for coming. You guys enjoy your break. I won't see you guys Friday. Remember, we're not having a discussion, but stay safe out there. And I will see you guys after the break. Thanks.
Thank you.
Thank you.